Hello and welcome to our October virtual chapter meeting for the Performance Virtual Chapter. Welcome, glad to have you with us today. We look forward to the presentation. I'm your moderator, Leslie Weed. Our Twitter for the virtual performance chapter is listed. The hashtag, our website, discussion list, email. Please feel free to reach out to us if you have any questions in the future or feel like presenting. We're always looking for presenters. Just a little bit about our webinar, GoToWebinar. If you have not participated in one before, you will notice you have a little help screen within the webinar. And if you require assistance, please feel free to raise your hand and I will chat with you virtually behind the scenes to try to help you. You can maximize your screen at the bottom. And then you can type in questions and our speaker today will be responding to your questions as best as possible. This session will be recorded and posted on our website for later. Also, big call out for our chapter sponsor, SolarWinds. They will be giving out a $100 Amazon gift card to one of our attendees today, and we will have that posted later also. So a big thanks to SolarWinds for their support. Hopefully, we'll see a whole bunch of you at Summit next week. So that is coming up. If you still have not registered or plan to register there, you can use our discount code. And this is a fantastic time. I hope to meet lots of you there. And our today's presenter today is Kenneth, and he's going to be talking about index strategies and good physical designs for performance tuning. So Kenneth, I'm going to go ahead and switch this over to you, and you will be able to take it away.
Thank you, Leslie. Just let me know if everyone can see my screen properly. It's the presentation right now.
Yep, looks good.
Awesome. So welcome to thank you for having me here. Today, like Leslie was mentioning, we were going to talk about index strategy, good physical designs for performance tuning. Like Leslie was saying, my name is Kenneth Ureña, and data platform MVP, and I'm part of the Linchpin People team. In case this is my blog, there is just one catch here is my blog's in Spanish, since I'm Spanish speaker. This is my Twitter, and like usual said, I always answer. The thing is I don't answer right away, but I promise I always answer. And part of the things that I do is I'm one of the runners of the past virtual chapter in Spanish. And in case you are interested in some Spanish, that is the Facebook page that we announce everything. What we're going to see today is something really important when we're trying to understand performance tuning is the journey of a transaction. What are the performance degradation factors? Physical designs. But when we talk about physical designs, we want to mainly talk about storage and rates. So we are going to be talking about no self-handled storage like the smart storage, like the big NetApp or something like that. We're talking about the small ones that you need to configure the rates and decide how many disks you're going to have in the RAID in order to present it to the lab. Then the basic indexing part, what affect our SIGs when we want to SIG, what is implicit conversion, how that affects us on our indexing strategy on our coding. And finally, coding best practices. That's what we want to cover. So that was a long introduction. So let's get into what we really are here. So what is the journey of a transaction? Like we were mentioning, like lots of people know, is SQL Server or the database itself is composed of two main files. It's the log file that you can see the log file like a dimensional array, where you have small cells. And SQL Server would actually call those cells virtual log files. So SQL Server write to the one that is empty or the one that is the actual that is writing all the information, and then when it's full, it goes to the next one that is empty. And then when it goes to the end, it have two choices: either go to the beginning if there is a space in the beginning, or expand the log file. So that is more or less how log file works. One of the interesting to take here is the log file present a data access pattern that is called sequential access. So you see it go to one cell to the next cell. It just work with one active at a time. In SQL Server, you can define if you want 20 log files, but SQL Server is just going to use one at a time. So when it fills one, it moves to the next one. The recommended RAID array for this is a RAID 1 or RAID 1 plus 0. We're going to talk about RAIDs later on, so don't pay too much attention to that. And the instruction to generate I/O on that file usually is a commit or a backup log. That is the two most important things to generate some kind of interaction on that log file. The second one is the data file. The data file, SQL Server writes and reads whatever it wants, and so that gives us a different kind of data access behavior or data access pattern. It is called random access. So you can have multiple database files active. So that means if you have 10 of them, if SQL Server has to read for the 10 of them, it will read for the 10 of them at the same time in parallel. The recommended rates is 1, 1 plus 0, 5 plus 0, or 5. Usually the most common one for an OLTP kind of transaction is 1 plus 0. What generates traffic on that is a checkpoint, a backup, a load or unload on cache. So there's more or less a small description about how SQL Server is it handles the different data files that the database have. Now let's see how actually work on the scenes. Is when you have one second. Here we go. So imagine you have to do an update on a specific page in memory. So what SQL Server will do is it will load the page from the data files. Once it happens in memory, it will update the page. Keep in mind that is still happening in memory. And then when it detects a commit, that commit will trigger to save information on the BLF. And it will download the information from the memory on the BLF to the drive. One thing to mention here is that there is some slight change that got introduced in SQL Server 2014 with a feature called delayed durability. They actually will give the control back to the application or to the requester before the commit, and you have the delayed durability activated for that specific database. So usually if you don't have that that feature activated, SQL Server will return the control to the application after the commit has completed successfully. Another thing to clarify is with the feature called in memory OLTP, there is some confusion going around that said that they make people think that SQL Server doesn't work in memory, and it just with this kind of a slide we can show you that it works only on memory. So in memory OLTP have more than just in-memory tables. Is kind of a blocking improvement for memory-based tables. So here we have cleared that everything in SQL Server works in memory. That is what usually most DBAs said. I want the much quantity of possible memory for my box. That is why. Okay. So then later on, that page gets sent to the data file once the control has given back to the application. Then later on, the laser writer with a checkpoint will take all that information to the data files. There is another important thing here to understand is what data integrity means. From the SQL Server perspective, data integrity is just based on the combination of data and log file. So doesn't mean that you have just the data file. No, in fact, it means if you have just the data file, maybe your data is not complete. So some information from the log file has not been completely applied. There's something to keep in mind when you try to work with different parts of SQL Server. Now, keep in mind that configuration, how data files work, how log files work, what kind of data access pattern affect each of them. Now let's take consideration what the greater performance or how we see it. Usually in database we have two things, right? Is the hardware and the software. But problems on the hardware actually will degrade the performance of the software, and about coding on the software will overload the hardware, showing performance issues on the software itself. They will degrade the software. So that is the internal battle, right? Is on hardware we have the CPU, memory, storage, and peripherals that we can affect our performance. And in software, it's data and algorithm. And this is a good thing. It's like that is not empty database that will perform slow. So data actually play a big place about where the performance degradation is located. And of course the algorithms. It's like if you're looking for a seek and you're using scan data access pattern, that is going to degrade your performance in your database. Okay, storage. Well, we're going to focus, just get back to the previous slide. We had shown, or the industry had shown really great improvements on CPU, memory, and performance. With storage, the storage basically has been stayed the same since ages. So we still having just the 15K RPM. We go from SCSI to SAS, but it's still the same kind of storage, with the difference, of course, of SSD that is just coming out of the market, but in a really huge price. So that is where we're going to focus on the storage part. Usually, the storage, we can see three different kinds of hard disk. That is SATA, SAS, and SSD. The difference is the slower one is the one on the left, and the faster one is the ones on the right. There is a huge performance difference between sequential I/O and random I/O, especially when we're talking about mechanical drives like SAS and SATA are. There is basically one disk that is spinning. IOPS means in-out per second. It's like how many operation of in and out per second can I get from that drive? How do we estimate the I/O for a specific hard drive? This is the formula. And by the way, I didn't invent the formula. Right on the bottom of the presentation is where the information and where that formula was taken from. So, but I have been using that in order to estimate the IOPS they're going to need for a specific database. Okay, so if we go to the website and to this specific Seagate Cheetah hard drive, it presents to us this information. That is the average read seek time, average write seek time, average latency. Then we can have the seek time for the formula, and then our IOPS estimation will go from around 126. This IOPS estimation is for random access. And the big question here is, what is the difference between random access, like the data files does, against the sequential access? And the main difference is, since the spindle is spinning, it have a head. That head have to move around. Moving around, that is called, an effect is called head seeking. So for example, imagine you have to read, I don't know, 100 pages, just to give an example, and you read one page at a time. So if the 100 pages are split between different places of the hard drive, the head have to move to the exact location while the disk is spinning, then read that page, then move again, then read the other page, and that 100 times. That is called random access. Sequential access is when the head moves just once and then read all the way on until they have all the information in it. That is called sequential access. As you can see, there is a huge difference between the performance they take to the head to move against the performance they take to move once and just read. And that is why the difference, that is why the effect is called head seeking. Okay. Now, different kind of rates we're gonna see is rate 0, 1, 5, and 1.0. The other ones 5.0 can be derived from from those for those. And rate 6 is basically a rate 5 plus additional drive. So what is a rate 0? It's called stripping. Okay, and usually in a rate 0, you have the quantity of disk, and then you multiply by the I/O estimation, and that is what the IOPS that you're gonna get from the logical drive. The site it will present when you decide to go to the rate 0 is the quantity of drives you add to the rate 0 multiplied by the size per disk. So what is the pros? The pros is high performance, because what it does in rate 0, what it does is it go to the information will go to the virtual drive, and then internally it will get one part of the data to one drive and the other part of the data to the other drive. So it is split the data between two drives. So it will double up your speed. And for cost, meaning is this kind of drive with this kind of rate will mean for example for the business guy that we are utilizing all our storage, so it's cheapest. One of the cons is fault tolerance. So what happens if you lost these two? Basically, you lost your entire virtual unit. Why? Because there is not redundancy anywhere. That is rate 0. Please don't use it in SQL Server. Rate 1. So rate 1, you can estimate the IOPS in this way. You take the quantity of this that you're going to add to the rate 1, divide by 2, and multiply it with the IOPS estimate. So in this case, if we have two drives with 126 IOPS. Rate 1 will provide me just 126 IOPS. The size is, for example, if we have two drives of 100 gigabytes each, the rate 1 will provide me a virtual unit of 100 gigabytes. Why? Because the way the rate 5 works is, if I receive one data to store, it will store one copy in one drive and another copy of that of another drive. That is why it's called mirroring, because it mirrors everything. Pros, fault tolerance. Of course, if I lose one of them, my virtual log drive will continue working because I have another copy in another drive. So the maximum quantity of drive that I can lose is 1 in this case. Cons, higher cost. It's like having an additional drive just sitting there waiting in case of something wrong goes on. Rate 5. This is where the things start getting funny. A rate 5 works in this way. It's when you receive a data, for example, let's say you receive 1 and 2, it will store one data in one drive, the second data in the second drive, and in the third one, in this case, it will create something called party. So parity in binary is like, for example, 1 plus 1 is 0. So parity should end up in 0. So in this case, if you put 1 and then put 1, parity is going to be 0 because 1 plus 1 is 0 plus 0 is 0. If you put 1 and 0 and talk about bits, then 1 plus 0 is 1 in binary. The parity has to be 1 in order to match up this 0 parity. That is how RAID works. So it adds an additional step to the saving information, that is the parity check. One of the things how you calculate the IOP estimate is, first, in order to do a RAID 5, the minimum quantity of this you need is at least 3. How do you calculate the IOPS estimate? Is the number of this minus 1 plus and multiply by the IOPS estimate per disk. So we're talking about 176 IOPS per sec per disk. We are actually talking that a RAID 1 will provide me, a RAID 5 will provide me 352 IOPS in the logical drive. Fault tolerance is one of the pros. Why? Because if I lost one of the drives, I still the other two with data, and I can calculate the information based on the parity that is expected. That is why everything has to match a parity check. In this case, is 0. It's cost-effective. That is called the cost-effective kind of drive, because actually it's not like RAID 1 that you have one drive just sit there waiting. You actually is for example, is like 1/3 of a drive is what you are sacrificing for the entire unit. And cons is when it's a failure, when you lost one of the drive, the RAID comes in something called degradate mode. So basically, every read that you have to do, every read that you do to the drive, it will actually generate a parity calculation. So in order that you can get the information how it is, and in the same way happens when you write to the drive. So basically, the performance of the storage cell will come to the floor, will go to the floor, and then your application will be performing really bad. That parity calculation in case of RAID failure is what actually kills the RAID 5. Then once you have to, when you remove the failure drive and you replace with another one, everything has to be recalculated. That is the rebuilding mode of the RAID. Then it comes another one that is really interesting, that is called the RAID 1 plus 0. RAID 1 plus 0 is basically what you will need at least 4 drives, and basically have a RAID 1 on the bottom, and then a RAID 0 to load balance. So the nice thing is, it's a combination of the 2 RAIDs. So you get the speed of the RAID 0. For example, you have to write 1 and 2. It will get 1 right to the first mirror, and then 2 right to the second mirror. So in order to get the estimates of for the RAIDs, for the IOPS of the RAID of the virtual unit, is the number of this divided by 2, multiplied by the IOPS estimate. So basically, if I had 4 drives of 176 IOPS per sec each, the virtual drive will provide me 352 IOPS in total. The size that will get presented to Windows is in a RAID 1 plus 0 is the quantity of this divided by 2 multiplied by the size disk. So if I have 4 drives of 100 gigabytes, Windows will see in a RAID plus 0 200 gigabytes size unit. Pros is fault tolerance, and this is where it gets interesting. So what happens if I lose these 2? Absolutely nothing, because I have a mirror that is this one. So that now is when you start playing with luck, right? So you have the potential. So you have the potential to lose one. You have the fact that you lost one drive, everything's going to be fine. But if you lose a second drive, depends what you lost it, you can still beat up, right? Because if you lost these two, and then these four, there are two mirrors that will back you up. But if you lose this one and the two, then you are done, because there is no more redundancy. So basically, in a RAID 1, you can lose you can lose one drive and have no issues, and you have the potential that maybe you lose another one that is not related straight with the RAID 1 the one you lost, you will be fine. The other nice thing is that it's not a parity calculation when you rebuild. If you replace the failure disk, you just copy the information from the previous one, and that's it. It's a really quick process. Okay. Any questions regarding RAIDs? No questions. We move on. So in the data files, something I want to recap is data files have a random access kind of data access pattern and can have multiple active. Log files have a sequential kind of access and just one active at a time. Physical designs. What a physical design is basically choose the right RAID for database file and split the files in order to get the expected access behavior. And that is all you have to do in order to get the right sizing. But this thing sounds really funny, right? Having that kind of physical design is like everything we need to do, right? So let's run some scenarios here. Let's go to scenario one. It's you have one user database with high OLTP traffic, high 10 dB consumption, and 60 cores kind of drives. How would you design a physical design thinking on RAIDs based on this specific need? What about something like this? I will put 10 dB and the data files of 10 dB in a RAID 1.0 in a SAS. The data files of the user database will go to the RAID 1.0 in a SAS. The log file for both databases will go in the RAID 5 and the RAID 5 using SAS. Well, there is some things to consider, right? RAID 5 will do parity calculation. That will degrade your performance, for sure. Now, we're talking about high traffic OLTP, right? We're not talking about low traffic. The other thing is, what is the most important drive for SQL Server in order to keep everything up in the speed? It's the log file, right? Because you remember, all the commits go straight to the log file. It doesn't go to the data file. It goes straight to the log file. So if I am talking about a heavy OLTP, having log file in RAID 5, it has the potential to have some degradation on our general performance. So let's eliminate the RAID 5 and let's have a RAID 1.0. Now, what was the problem on the random access pattern? It's basically the head seeking. So what happens if you have two highly intensive files? They have a data access pattern that is sequential, writing to a single drive. It's very likely going to have exactly the same behavior of a random access, right? Because the head is going to be moving from one way to another in order to hook up to the need. So maybe having both log files to the same SAS unit is not what we have to do. So now the final suggestion is, well, I'm not happy to have it log file. of both databases. Now I'm going to put the data file on the same drive. So how it works is we will change the drive for SSDs. This is the thing behind it. What do I need for 10DB in an OLTP kind of database? I just need a lot of IOPS. What do I need for log files? I just need a lot of IOPS. It shouldn't be like kind of a huge file. So basically, if I move everything to SSD drive doesn't have the head syncing problem. So basically, it will be for the scenario we're seeing, it could be one of the best solutions and one of the cheapest, because it doesn't have to have, in order to have the same performance on SSD that I have with SAS drives, I would have to add a lot of drives in random access. There is some pros and cons that we need to consider when we use SSDs. Is the lifetime of the drive that is smaller, usually is smaller than SAS, but it's something that you have to check with your vendor in order to understand how long those drives would last compared with SAS. And scenario 2, multiple user database, high OLTP traffic, high TimeDB consumption, multiple core server. So basically the goal here is try to get it thinking into what a possible design for that kind of a scenario will be the best. So this is one way to start thinking. It's like the first initial proposal that for sure can be improved, but I just wanted to get you thinking about how can I improve this in order to have the best performance based on the cost restrictions. So try to keep the costs small and try to have high performance. Indexing. Okay. We can talk about indexing without talking what a table structure is. The table structure in SQL Server, and that is taken actually from SQL Server 2008 Books Online, this picture, is basically a table. If it's a partition, it's a set of partition, minimum of 1. Then that set of partition have a combination of heap of bit tree. Then we're going to see what a heap of bit tree is. And then the heap of bit tree contains data, lobs, and row overflow kind of pages. So that is what a table is. Now, if we talk about heap table, basically what we are talking about is trying the aim page and then all the rows included, and then like kind of you want to see it like it's a forward and back pointers to each table. A cluster table is based using a B-tree kind of a structure that you have your root index or your root page that will point to the child of the other two root pages, and then each page have a pointer back to the previous one and a pointer to the forward one, to the next one. So like saying is like every page have a pointer to their next siblings. Then every page on the final root level have a pointer to the data rows. So basically, if you have well, we're going to see an example of how this looks on a more or less on when you insert data. But when you run scans, what you basically are scanning are the data pages, the final data pages, or the final leaf pages. Everything that is not a leaf pages is a root page. There's another thing to keep in mind, just that every cluster index must, every B-tree index must have just one single root page at the top in order to point everything. Now, imagine that you have this information that you introduce for one table. You have one and Mr. Adam Taylor. So I said his name is ID and name, full name. So how you cluster, you define your cluster index, your B-tree index in this case, that you're going to use ID. You're going to use ID. Then the ID get introduced on the root pages in order to have an idea of where to go when you have to find information. And then the data itself will go to the lift pages, to the data pages. What I'm trying to show here is the cluster index is the data. There is no doubt about it. The cluster index is the data for sure. Non-cluster. Non-cluster is based on B-trees as well. And it have the same thing, two levels. It have the root nodes. In the leaf nodes, there is something interesting. It have a pointer to the B-tree of the cluster or heap, in this case. So if we have a cluster, the cluster key get sent to the leaf node of the non-cluster, right? So what I'm trying to say here is, if you define your cluster by ID and you define a non-cluster by name, the leaf node of the non-cluster will have the ID on the leaf node. When you do includes, that goes to the leaf node of the non-cluster. So the non-cluster have the ID of the key definition for the cluster. You have that clear when you make your indexes or your queries. Column store is a base. It's a different story. So what we have seen about heap and B-trees is row-based storing. So every page have the entire row. In column store, the pages, instead of having the entire row, have the column, and multiple columns go to multiple pages. So it completely came to change our data storage management. Column store, even though it's a new feature, well, it's not that new anymore, but it got introduced in 2012. And the algorithm itself and all the information about column store, all the algorithms, were written like 25 years ago. So data access pattern, seek, scan, and bookmark lookup. Let's see what it does. What are those? Let's try to load the first demo. So basically, I'm using the database for Kimberly Trip. It's called Create, the Create database from Kimberly Trip. I'm trying to restore it to have a clear start. I'm changing the owner to, instead of be myself, to BSA. And let me see what else. I'm changing the compatibility mode to 12. So it's equals over 2014. So I'm still executing. It's weird. Okay, now I was able to restore the database. So now let's take a look of what a seek does and what is seek. So basically, well, let's turn the execution plan, and we're going to work on this database. There are simple queries. The table is the charts table. In the table we're going to work, and it has one cluster index defined on charts number and have 3 non-cluster index defined category provided and server number. So if I do this and I select the proper database, basically what it does, since charts number is the cluster index, basically what it does is a cluster indexing. So what it's doing is, under the scenes, is going to my cluster index going to my cluster index, I'm trying to find the number ranges, and then until it goes to the exact data. That is a cluster index seek. So that is what is called an index seek. Now, if I do a provider number, keep in mind I have a non-clustering provider number, what it does is an index seek. Exactly the same way of the cluster, but in this case non-cluster. Why? Because I have an index on provider number. Now, if I do the same query, but I add charge number, keep in mind that my non-cluster has only provider number, right? So when I execute this, I shouldn't expect this, right? In case if I don't, this is the proof of the cluster index value is in the leaf node of the non-cluster. You have the charge number. The charge number is the cluster, so SQL Server doesn't need to go to another place of outside that index to provide the information required, because the information is in non-cluster index itself. Even that I define the non-cluster to have only provider number, right? Let me just load the indexes here so you can actually see them and make sure I'm not tricking you. Right? So you have provider number. Now what we see, and there is not charge number defined keys. If we want to go and check the data, the table itself, you're cool. So now what happened when I do this? Right? Charge amount is not part of the index. So you have to go to the cluster using the cluster number reference and do a key lookup, what we call a key lookup. In this case, a key lookup because it's a cluster. So look, the interest part here of this kind of change is what is costing most on this query. So the key lookup, is what is costing most in the execution. Is this a problem? It's not a problem. It would actually depends, right? But this is clearly when you're having issues on parameter sniffing. This is a clear behavior of that you want to get rid of in case that you have parameter sniffing issues. Why? Because there is nothing more slower than a seek that should be scan instead of seek. So in case you want to fix this, we can add this and this. We can change the index, the one that have provider number, to add the charge amount. And then once that is done, SQL Server, we have all the information that you need in the index itself, and don't have to go to do the cluster index lookup or the key lookup. The other thing to consider, you see, it changed to index. The other thing to consider here is the main question here is the cluster index unique? Even the SQL Server doesn't force you to make it unique, under the scenes, if you define a cluster index that is not unique, it goes to a step called the make unique the cluster index, because that reference for non-cluster have to be unique. Actually, what it does, for example, let's say you define a non-unique cluster index and you define it with a small int. The additional part to make the cluster index unique is going to be an int part that is an incremental. For every time you insert 2, it will increment by 1 until you hit the maximum int number. There's actually a really funny error that's called the 666 error in SQL Server. This is when you run out of unifiers for the specific entries of the non-cluster, of a cluster index. Sorry. So now let's move forward to what a scan should be, or how we work on the scans. So we are working on the member table. of course, from the right database. We have the member table, and the member table has a cluster index defined on member number and two non-cluster, on card number, region number. So if I'm going to do a search and filtering of first number, what SQL Server is going to do? Let me turn on the execution plan. Saying I don't have a non-cluster index defined over first number, it's going to generate a cluster index scan, right? Why? This is what it's going to do. I don't have a non-cluster, so I have to scan. The cheapest thing to do is to scan the data instead to go one by one over the cluster. So it will go to the leaf level node of the cluster in order to get the information. Now, let's say we say, okay, let's have an index. Let's add an index of the first name, so we have a non-cluster here. All right, so let's try to do. One sec. I have to do one small change. Right. So we have created that index. So let me just show you the index. Right. We have the first name, the card number, the member number, the cluster, and the region number. So if I go and execute this query, we should expect an index seek, right? But we get an index scan instead of an index seek. Why? And this is one of the things that is one of the most difficult things to find on SQL Server when you have facing performance tuning issues. This is called an implicit conversion. The first name is a varchar column, and it's sending an nvarchar column. Since the columns are different, SQL Server is not able to use the index how it is. So in order to fix that, well, in this case it's pretty easy. To be honest, we don't have to add index and anything. Just make sure they are exactly the same kind of columns. So if I remove the nvarchar kind of column and make it exactly the same of the column type, it will do the indexing. So of course I'm doing a KeyLookup because I'm requesting most columns than just the first name, but I can do just first name, and then it will actually return an index seek. So this implicit conversion thing that I'm talking about is exactly the same like you do something like this. It's exactly the same instruction. This implicit conversion is how an explicit conversion should look like. Is the index scan. If I execute this in this way, it's exactly the same index scan. So when you see something in your code that is casting a column in order to compare with a value, maybe the best way to do it is to don't cast the column and cast the value, if possible. That should return an index seek. Okay, and then Let's move to the presentation again. Coding best practices. That thing about adding the column need for the non-cluster is called index coverage. So in order to avoid non-cluster, if there's necessary, it's not necessary. It actually depends about the situation, but most of the time you want to increase the performance of a specific query. Doing coverage specifically, you have you have the issues on the if you have issues in performance, it will help you a lot. A conversion, even is implicit or explicit, if you don't take care of them, the performance of the database, doesn't matter how many index you add, will not get fixed. SQL Server is designed of a mathematic thing called that is sets management. When you do cursors, the cursor is basically a row by row kind of access, so that will get really, really slow. So if there is no way that you can avoid using cursors, then there's some use case for cursors, but most of the time they're just overused. Sorting. You need to sort the data in order to do joins. That kind of create a problem or additional problem performance. So you can use indexes that are sorted exactly in the same row. That will increase the performance itself for the query. And choose the right index to the expected data access pattern. That is more or less what the code best practice will be. So Leslie, I think that I'm done with this, with the presentation. I don't know if there are more question answers or any question answers. That was clear. It was very confused.
So there was just a couple questions. Data log and temp disk, thoughts on disks for indexes, and you might have covered this.
Pardon
me? For data log and temporary disks, do you have any thoughts on disks for indexes? Hi, Kenneth. Can you still hear me?
I can hear you.
Okay, great. Sorry, little audio difficulty there. Were you able to, did you want me to go ahead and read through some of the questions for you, or?
Please, I will really appreciate it.
Okay, sounds good. So one of the questions was for data log and temporary disks, thoughts on disks for indexes?
Okay, data logs and temporary disks. So when you say temporary, is like talking about temporary tables or
I believe so. So temporary files, so data log and temp files for the disks. Thoughts on disks for indexes?
I will say that mostly in TempDB you are talking about OLTP. Everything is going to depend about what kind of traffic you are talking. You are talking about OLTP kind of traffic. If you have if you can get SSD, that will get you the optimal performance because the kind of access. So if you want to put the log files, usually keep in mind the log files are they use the sequential data access pattern. So if you cannot get SSD, they remove the head-seeking kind of pattern. The best way to put it is to put it in different spindles so that they don't get into the random access that will decrease heavily your performance. So it will depend, actually, it will depend about the budget, and it will depend about what you actually can get. Keep in mind, we're talking about the small kind of arrays, these arrays. We are not talking about the big net apps. They have hot areas and cold areas. Did that answer the question? Leslie?
I believe so. I believe so. Here's a comment for you. He really liked the graphical slides. He finally understands the clustered versus non-clustered indexes. So a big thanks to that, Kenneth.
Pleasure.
Uh, let's see. One other one. He understands loading the cache, but what is an unload of the cache?
When you have when the SQL Server is running on memory stress, there is one controller is called the PLE, the page life expectancy. When SQL Server is running on stress, memory stress, it have to unload pages from memory to the disk, pages that maybe are dirty or they are not clean. So that we actually have to write the data into the disk. That is more or less what unload the cache is. So something, if you are measuring the SQL Server performance, something that you need to keep an eye of is on PLE. That is plenty blog posts talking about what is the right value to keep in mind, because the closer you get to 0, the slower your system is going to be. So unload the cache is take the pages that are in memory and send it to the disk. Most of the time is because memory stress.
Okay. One other question. When my company cannot afford RAID 1 plus 0, what RAID disks are recommended for data and log files?
If the company cannot afford RAID plus, well, there is just RAID 5 available, right?
Yeah.
You cannot get near one plus, and just RAID 5. The only possible answer is RAID 5. But if I can try, I will try to fight for RAID 1 at least for the log files, because in case of my RAID 5 go into degrade mode, that is a behavior that doesn't have the RAID 1. So at least I will be able to recover quicker or affect a little bit less the operation itself. But we are talking about we're talking about OLTP kind of traffic, no OLAP kind of traffic. Usually in OLTP kind of traffic, you would really want to focus on your log files more than in your data files. But like I said, this is like a general suggestion, but we need to take a look at the specific details in order to make sure that it's the right solution for my need. Does that make sense?
I believe so. So here's another good one. How do I deal with SAN data placement? The SAN admin tells me it doesn't matter where I place the data indexes.
Well, the SANS admin is always going to say that, right? They don't want it to get us into their storage. The best way to do it is sometimes it's difficult difficult not. It is a little bit. It takes more effort to deal with SAN administrators sometimes. The best thing they can do that is this speed kind of application that is the replacement of SQLIO. They will measure your latency and will measure the bandwidth you are getting. So SANS guys likes to hear the information on IOPS. Like, I'm gonna need this many quantity of IOPS. So once you talk to them on that language, they will say, all right, this is what I have to do. But sometimes talking with SAN administrator is a little bit more tricky, and the only thing that you have to do is try to get the IOPS that you need for your drives. If they say they want to put everything in the same place, just just run a stress test on your system and measure how many IOPS you need and send that information to him and say, look, this is the information I need. Either you provide me the IOPS or you provide me the different logs. At the end of the day, what you really care is the IOPS you can get from the drives. That's it.
Okay. And what about the NAS?
NS?
NAS?
I'm
not sure on that one either. Okay. Here's another question. When you say one active log file, do you mean one active per core?
No. Log files are sequentials. They don't work in parallel. So SQL Server, if you have 10 log files, SQL Server will write into one at a time. So when it fills one, it will go to the next one. That is different behavior from data files. Data files, there is some nice formula about how many files should I get, but for log files, it's sequential, it's not in parallel. So usually what I do is I take care about with backups and everything about always having enough space, but usually one file is more than enough. The only way that I see that it kind of makes sense to have an additional drive, an additional log file, is to prevent my first log file run out of the space and for whatever reason in a heavy OLAP traffic. But for OLTP kind of traffic, one log file should be more than enough.
Okay, so back to the question about the NAS. They were talking about a NAS, network attached storage. Yep.
What's the question about NAS?
So probably the same question is where to place the data indexes in that scenario.
And at the end of the day, what you want to measure is the IOPS, right? So if I don't have I don't have the luxury of a smart array and smart storage, I will always like to keep log files separate from data files because they have a different data access pattern. So I like to keep the sequential alone, so I don't have to invest a lot of money on drives for the sequentials kind of drives. In this case, are the log files. The data files, and they are random. If you are more random, it will continue being random, right? So you can keep your data files in same units and the log files completely separate. That is my initial suggestion. But at the end of the day, what you really care is the IOPS you get out of the system.
Fantastic. Okay, and last question. This is a follow-up to the core question. Why do folks suggest one file per core?
Well, that will depend about the quantity of cores that the server have. But if you are talking about log file, I don't see any benefit on it. If you're talking about data file, there are some kind of benefits, especially on 10dB and on the database itself on the data files. But if we are talking about log files, one file per core, it will not add any value.
Okay. Fantastic. I hope we got those all answered for everyone. We will have the recording and the slides on the Virtual Performance Chapter site. Kenneth, thanks so much for joining us today. We really appreciate your time and hope to meet you at Summit next week.
Absolutely. Thank you very much for inviting me. It has been a pleasure to talk here. I hope everyone enjoyed the presentation.
Sounds good. Thanks much. Bye, everyone.